Marko Ivanova. In this video, I will talk about the general form of the equation of a circle. We'll start from the center radius form of the equation of a circle, with center C, a point with coordinates h and k, and a radius of r. This center radius form is x minus h to the second plus y minus k to the second is equal to r squared. Let's square each of the binomials and also move r to the second to the left side of the equation. The square of difference of two terms is equal to the square of the first one minus twice the product of both plus the square of the second term. We apply the same formula for y minus k to the second, and we move r squared to the left side. Now let's rewrite the equation, and the second term is the term of x, it's the next term, so I write in parentheses its coefficient. It's minus 2h times x. And we do the same thing for minus 2k times y. And there's one numerical term that I have written with the other at the end of the left side. Let's rearrange the terms. We write in the beginning the x squared and y squared, the highest degree terms. Then the first degree terms, the x and the y term, and then the constant terms. And let's name the coefficient of x with c, the coefficient of y with d, and the constant term with e. So the equation will have the following form: x to the second plus y to the second plus c times x plus d times y plus e is equal to 0. This form, where the terms are arranged, second degree, first degree terms and 0 degree terms, is called the general form of the equation of a circle. I said a general form of the equation of a circle because we just started from the center radius form of the equation of a circle. If we take any equation of this form, then it could be an equation of a circle, but its graph could also be just a point, or it could be non-existent. We'll see when this will happen. Starting with an equation in general form, we can complete the square to get an equation of the following form: x minus h to the second plus y minus k to the second is equal to a number m. This number could be positive, 0, or negative. It depends on the given equation in the general form. The first case is to have a positive number on the right side of the equation, m to be positive. Then we can use it for the square of a radius. So the square of the radius will equal to m, or just the radius will be square root of m. M is positive, so square root of m will be a real number. So this equation will be an equation of a circle, which center has coordinates h and k, and the radius is square root of m. The second case is to get 0 for m. If you substitute here m with 0, we'll see that the sum of two squares is equal to 0. It will be possible if and only if each of the squares is 0, or x minus h should be 0, and y minus k should equal 0. And it means that x will equal h, and y will equal to k. So what we get? We get just two single values for x and y. So in this case, the graph of the equation is just a single point with coordinates h and k. The third case is when m is a negative number. If instead of m we have a negative number, we see that on the left side of this equation we have a sum of two squares. So the minimum value of this sum can be 0. And on the right side we have a negative number. There is no way this statement will be a true statement. Then no points satisfy the equation and the graph is non-existent. Let's solve the following example. Decide whether or not the given equation has a circle as its graph. If it does, give the center and the radius. If it doesn't, describe the graph. We have to change the given equation to the following form. On the left side, sum of two perfect squares. Note that in this form, if you square back, you'll get x to the second plus y to the second. We have 2x to the second plus 2y to the second. So we have to divide both sides by 2, both sides of the equation by 2, to make those coefficients of the second degree terms 1. So we'll get the following new equation. X to the second plus y to the second plus 7x plus 3y plus 1 is equal to 0. Now let's rearrange the terms. I will write the x terms in the beginning and then the y terms, and I will move the constant term 1 to the other side, so it will be negative 1. Our goal is to complete the x terms to a perfect square trinomial and to do the same for the y terms. We have the following formula for a perfect square trinomial, the following form of perfect square trinomials. A to the second plus or minus twice ab plus b to the second. Those two trinomials are called perfect square trinomials. They can be factored as a plus or minus b to the second power. So I'll state this in the following way. We have the square of the first term plus or minus twice the product of both terms plus the square of the second term. This is equal to the sum or the difference of the square of the first and last term to the second, of the first and last term to the second power. Okay, now I'm going to represent the first x squared as x to the second power plus twice times the first term x plus, we can discover from here the second term of the perfect square trinomial, because the product of twice the first and the second should be 7x. We know that the first is second, so I get 2 times x times what will be the second term. We can see it from here. It will be 7 over 2. So after you multiply back 2 times x times 7 over 2, we'll get exactly the middle term, 7x. So we see the missing term of this trinomial, so it could become a perfect square trinomial. The missing term is 7 over 2 to the second power. When we add an number to one of the sides of the equation, we must do it to the other side, so I can keep the equation in balance. Now we'll continue to work with the y terms. We have y to the second plus, I should write in parentheses, the first term to the second, plus twice the product of the first times what will be the second, so we can get, as a result of this product, 3y. The second term must be 3 over 2. By the way, if this number in front of the term is 1, then the second term of the perfect square trinomial will be always 1/2 of this coefficient. 3 over 2. So we have to complete the perfect square trinomial by adding 3 over 2 to the second power. So we add here 3 over 2 squared. We add it to both sides of the equation. Now on the left side we have two perfect square trinomials. the first one can be factored as a perfect square. It is x, the first term, plus the second term to the second power. Say the first plus the second to the second power. So I get x plus 7 over 2 to the second power. And the second perfect square trinomial can be factored as y plus 3 over 2 to the second power. So I have the first term y plus the second term 3 over 2. And we have to simplify the right side. 7 over 2 to the second is 49 over 4. And 3 over 2 squared is 9/4. We have two like fractions on the right side. We can add them. 49 plus 9 is 58 over 4. So on the right side we have minus 1 plus 58 over 4. I will do it on the side. Minus 1 plus 58 over 4. But minus 1 could be expressed as negative 4 over 4. So as a result, we'll get 54 over 4 for the right side. On the left side, instead we have x plus 7 over 2, we can express this x minus negative 7 over 2, and here y minus negative 3 over 2. Now let's compare this form to the one that we have on we talked about in the beginning. We see that the left side is the sum of two perfect squares, and the right side of this equation is a positive number. So I can use it for a radius of a circle, and this equation will be an equation of a circle, which center is a point with coordinates a negative 7 over 2 and negative 3 over 2. And the radius is square root of this number, square root of 54 over 4. We must simplify this square root. So using the quotient property of radicals, it will equal to square root of the numerator, 54, over square root of the denominator, which is just 2. And 54 is the product of 9 and 6. So I get square root of 9, which is 3, times square root of 6 over 2. This is the radius. As one more example, we have the following equation. We rearrange the x and the y terms first, and then the numerical term should be moved to the other side. Now let's complete the two perfect squares. From the x term, we can discover the missing second term of the perfect square trinomial. We have the square of the first plus twice the product of the first times the second, so the second will be 2. We need to add 2 squared to both sides. And for the second perfect square trinomial, we can discover that the missing term is 2, because 2 times y is exactly 4y. So we need also to add 2 squared to both sides to complete the second trinomial. The first perfect square trinomial can be factored as x plus 2 to the second, first plus second squared. And the second perfect square trinomial can be factored as y plus 2 to the second power. And we have to work on the right side. 4 plus 4 is 8 minus 8 will get 0. So the number on the right side is 0. On the left side we have sum of two squares. This equation could be a true statement if and only if each of the squares is 0. So x plus 2 must be 0 and y plus 2 must be 0. Or x is equal to negative 2 and y is equal to negative 2. Only one ordered pair, negative 2, negative 2, will satisfy this equation. So the graph of the given equation is just a single point with coordinates negative 2, negative 2. If you solve a problem and the right sign becomes a negative number, then there is no way to add 2 squares to get a negative number. In this case, the graph of the equation will be non-existent. There is no such figure.